for the inverse of the original function, it is not necessarily a function. Give you an example. For example, y equals x squared. This is the simplest quadratic function. In the Cartesian plane, we can figure out the graph for this function. Here, this is the graph of the function y equals x squared. We can write it like this, fx equals x squared. If this relation is also a function, we can use f of x to replace this y. Okay? That you say this graph can pass vertical line test. Okay? So this relation is a function. From the previous discussion, we have known the function, its inverse, should be symmetrical over this straight line y equals x. Why? Because every point on the original function, the x-coordinate, y-coordinate should be reversed. That you say, on the original function, x, y should be y, comma, x on the inverse of this function. So every point we need to figure out its reflection in the line represented by y equals x. So for this point, its reflection should be here. This point is on the y-axis, so its reflection is just itself. This point is also on the y equals x, so its reflection should be itself. This point, its reflection should be here, right? Then we can figure out the graph for the inverse of the original function. It should be like this. Okay? Now, you know, we can use the expression that you say, we use x to replace y, we use y to replace x, then we can figure out x equals y squared, y equals x under the square root notation, positive, negative, right? Here, x must be greater than 0 or equal to 0. Here, for the original function, this y greater than 0 or equal to 0. X should be real number. Here, for the inverse of the original function, y should be real number. Now, you can find a secret. Here, the domain should be the range should be the domain for the inverse of the function. This domain should be the range for the inverse of the function. But here, we just say it's a relation. This is a relation, right? But this relation, in algebra, we can judge. For every x, we have two different y values. In geometry, this graph cannot pass vertical line test. Why? Because for any vertical line, except for this point, the vertical line test can be passed, because the vertical line just has only one POI with the graph of the relation, except for this point. The other vertical line has two POIs with the relation. So the graph cannot pass vertical line test. So this inverse is not a function, just a relation. That is to say, the inverse of a function is not necessarily a function. So you need to be careful about this. Now, if this function is a linear function, for example, y equals ax plus b, you will find out for this situation, its inverse should be like this. We use x to replace y, we use y to replace x, right? So x equals ay plus b, x minus b equals ay, y equals x minus b over a. Right? If we assume the original function's graph is like this, okay? Y equals ax plus b. Its inverse should be symmetrical over this straight line. So for this relation, the graph should be here. It should be like this. Okay, this should be y equals x minus b over a. This is the line y equals x. Now you will find out for this red line in algebra, you can easily judge for every x, we just have only one value to correspond to this x. In geometry, this red line can pass vertical line test. That is to say, for any vertical line, the relation represented by this equation just has only one POI with the vertical line. So in geometry, we can say this graph can pass vertical line test. So it should be a function. So we say, if the original function is a linear function, its inverse is also a function. So we say the inverse function, not just inverse of the original function. We say the inverse function. That's it.